In 2008, China produced fewer than 5,000 electric vehicles. 15 years later, that number exceeded 6 million annually. In 2000, Chinese companies held virtually no patents in 5G telecommunications. Today, they hold more than any other nation. In 2010, mobile payments processed transactions worth roughly $30 billion. By 2023, that figure surpassed $80 trillion. These transformations occurred within a single generation. The question that economists and policymakers worldwide now examine is fundamental. Why is China so advanced in technology? The answer involves strategic decisions made in the late 1970s. Educational investments that began decades ago, unique supply chain advantages, distinct consumer behaviors, and policy frameworks that created conditions for rapid technological scaling. This story spans multiple sectors, crosses several decades, and challenges assumptions about how technological leadership emerges. China's technological trajectory began with deliberate policy choices in the late 1970s. In December 1978, reforms introduced by Deng Xiaoping fundamentally restructured the nation's relationship with technology and foreign knowledge. The reform and opening up policy represented a calculated strategy to acquire technological knowledge through controlled exposure to foreign expertise. Foreign companies were invited to establish operations through joint ventures with domestic partners, ensuring Chinese engineers worked alongside foreign experts and absorbed technical knowledge. Throughout the 1980s, special economic zones in Shenzhen, Shuhai, Shantou, and Jiman offered tax incentives and regulatory flexibility to attract foreign manufacturers. However, the deeper goal was knowledge transfer. Chinese policymakers studied the industrial trajectories of Japan, South Korea, and Taiwan systematically. These nations had transformed from post-war economies into advanced technology producers within 30 years. Japan's absorption of Western technology in the 1950s and 1960s provided a clear template. South Korea's strategy of building national champions in electronics through coordinated government support offered another model. Taiwan's success in semiconductor manufacturing demonstrated how focused specialization could create global leadership. By the 1990s, focus shifted toward digital technology. The government invested in telecommunications infrastructure, expanded computer science programs, and created the Ministry of Information Industry to coordinate technology policy. When the Internet era arrived, China was positioned to participate actively. This multi-decade foundation created institutional knowledge, trained personnel, and established technology adoption patterns that proved crucial when the mobile internet revolution began. Scale in technology markets creates several advantageous dynamics simultaneously. Data accumulation accelerates, improving machine learning algorithms. Economies of scale drive down unit costs, making products more accessible. Network effects strengthen, where each additional user increases platform value. China possesses unique scale advantages. With over 1.4 billion people and a middle class exceeding 400 million individuals, the domestic market provides opportunities unmatched globally. When a Chinese technology company launches a new mobile application, it can reach 900 million smartphone users domestically. If adoption reaches 10%, that represents 90 million users. For comparison, Germany's entire population is approximately 83 million. In artificial intelligence development, Chinese companies access datasets of extraordinary size. Facial recognition systems train on billions of images. Natural language processing models train on vast Chinese language corpora. The volume of data enables rapid iteration and performance improvement. In electric vehicles, Chinese manufacturers produced over 6 million vehicles in 2023. This production volume creates economies that reduce costs across the entire value chain. Battery costs decline through mass production. Component suppliers invest in specialized equipment because order volumes justify investment. The scale advantage extends into supply chain density. In Shenzhen alone, electronic supplier concentration is unmatched globally. Hardware entrepreneurs can source thousands of components and visit supplier facilities within a single day. This density dramatically reduces time from prototype to production. On the other hand, scale creates coordination challenges across enormous distances and requires sophisticated quality control systems. However, Chinese companies have developed expertise in managing complexity at scale. The result is an environment where technology products move from concept to mass market faster than in most other countries. The technology sector depends fundamentally on human capital. China has constructed a talent pipeline of remarkable scale. Each year, Chinese universities graduate over 4 million students with STEM degrees. The United States graduates approximately 800,000 STEM students annually, and the European Union graduates roughly 1.2 million. China's output exceeds the combined total of the United States, European Union, and Japan. This emphasis reflects cultural and institutional factors. Chinese families historically prioritize education, particularly in technical fields offering clear career pathways. Institutionally, university enrollment expansion since the late 1990s specifically targeted STEM fields. Government funding mechanisms favor technical programs. University rankings reward research output. Scholarship programs prioritize engineering and applied sciences. Major Chinese universities have established deep partnerships with technology companies. Tsinghua University collaborates with Huawei, Alibaba, and ByteDance. Students participate in industry-sponsored research while enrolled. Professors consult for companies, ensuring academic research remains connected to practical applications. Research investment has grown dramatically. In 2000, China spent roughly $90 billion on research and development. By 2023, that figure exceeded $600 billion, second only to the United States. As a percentage of GDP, Chinese R&D spending now exceeds 2.5%, comparable to many European nations. Cities have emerged as innovation clusters with distinct specializations. Shenzhen focuses on hardware and telecommunications equipment. Hangzhou centers on e-commerce, technology, and digital payments. Beijing concentrates on artificial intelligence and internet platforms. These clusters create environments where talent, capital, and companies interact intensively. However, questions persist about innovation nature. Critics note that much Chinese research involves incremental improvements rather than fundamental breakthroughs. Transitioning from adaptive innovation to pioneering innovation requires different institutional cultures. Greater tolerance for failure, and reward systems valuing originality over publication volume. Nevertheless, the talent pipeline scale ensures China will remain a major force in global technology development. Manufacturing capability and technological capability are deeply interconnected. The ability to produce complex products at scale requires technical knowledge, process expertise, and systems integration skills that translate directly into innovation capacity. Over 3 decades, China built manufacturing ecosystems of extraordinary depth and density. The term ecosystem is precise. It encompasses component suppliers, materials producers, equipment manufacturers, logistics providers, quality control specialists, and skilled workers operating in close geographic proximity. In cities like Dongguan, Shenzhen, and Suzhou, this density reaches unmatched levels globally. When an engineer designs a new product, moving from concept to prototype typically requires sourcing dozens or hundreds of components. In most countries, this takes weeks or months. In Chinese manufacturing hubs, the same process occurs in days. Engineers can visit facilities, inspect components, and negotiate modifications face-to-face. The concept of vertical integration at regional scale explains much advantage. Different companies handle each production stage, but geographic concentration creates vertical integration benefits without organizational complexity. Battery manufacturers locate near electric vehicle assembly plants. Display panel suppliers cluster near smartphone manufacturers. The manufacturing workforce represents another critical asset. After decades producing electronics, vehicles, and industrial equipment, Chinese factory workers and production engineers have accumulated deep expertise in optimizing production lines, maintaining quality at high volumes, and solving practical scaling problems. This tacit knowledge cannot be easily transferred through documentation. The manufacturing advantage is particularly visible where rapid iteration matters. Electric vehicle companies can test new battery configurations quickly because the entire supply chain adapts rapidly. Drone manufacturers can experiment with new components because suppliers provide modified parts within days. Meanwhile, other countries have discovered that replicating this ecosystem is extraordinarily difficult. Building factories is straightforward. Recreating supplier density, workforce expertise, and institutional relationships enabling rapid coordination is far more challenging. China's approach incorporates long-term strategic planning through formal institutional mechanisms. The five-year plan system provides the primary framework. These plans identify priority sectors, allocate resources, and coordinate actions across government agencies. The current plan designates artificial intelligence, quantum computing, semiconductors, genetic engineering, and deep space exploration as strategic frontiers. These designations trigger concrete actions. State-backed investment funds provide capital to priority sector companies. Research institutes receive increased funding. Tax incentives encourage private investment. Government procurement policies favor domestic suppliers and strategic technologies. Infrastructure investment demonstrates the long-term perspective. China built over 40,000 kilometers of high-speed rail in less than 15 years. This investment required advances in materials, science, systems engineering, and construction techniques. Much technology was initially acquired from foreign partners, particularly Japanese and German companies. However, Chinese engineers absorbed this knowledge, adapted it, and developed indigenous capabilities. The network was not commercially viable in traditional financial terms. Construction costs exceeded $800 billion. However, strategic benefits extend beyond direct financial returns. The network connected previously isolated regions, facilitated economic integration, demonstrated technological capability, and created demand supporting domestic supplier development. The government also supports technology through procurement and market access policies. When government agencies purchase technology, they often prioritize domestic suppliers. For foreign companies, market access often depends on technology transfer agreements or joint ventures. These requirements have generated controversy and contributed to international trade tensions. However, from China's perspective, they represent a continuation of the knowledge acquisition strategy begun in the 1980s. The model combines state direction and market competition. Private companies compete vigorously but operate within a framework of strategic guidance and support. Technology adoption patterns in China differ significantly from Western markets, creating opportunities for rapid scaling. Mobile payments illustrate this dynamic clearly. In the early 2010s, China remained largely cash-based. However, within 5 years, mobile payments became dominant. By 2023, mobile payment transactions exceeded $80 trillion annually. For comparison, the United States processed roughly $1 trillion in mobile payments during the same period. Several factors enabled this rapid shift. The large youth population adopted mobile payments quickly. The leapfrog effect played a crucial role because China lacked entrenched credit card infrastructure. New payment systems faced less resistance. Super apps emerged as another distinctive feature. In Western markets, consumers use different apps for different functions. In China, apps like WeChat combine messaging, payments, shopping, transportation, booking, utility payments, and government services in one platform. This integration creates convenience and network effects, reinforcing user engagement. The super app model generates vast amounts of data about user behavior across multiple contexts, enabling sophisticated personalization. Delivery ecosystems in Chinese cities operate at remarkable efficiency levels. Food delivery typically arrives within 30 minutes in major cities. This efficiency depends on technology platforms coordinating millions of transactions daily and optimizing routing algorithms. Smart city initiatives have progressed rapidly. Cities deploy extensive surveillance systems using facial recognition, traffic management systems using artificial intelligence, and integrated urban data platforms. Implementation speed exceeds Western democracies, partly due to different regulatory environments and social norms regarding privacy. For technology companies, this environment provides rapid feedback loops. They can launch features, observe behavior across millions of interactions, collect detailed usage data, and refine products based on quantitative evidence faster than in markets where adoption is slower or privacy regulations stricter. China's technological rise occurs within intensifying global competition. In electric vehicles, Chinese dominance is clear. In 2023, Chinese manufacturers produced over 60% of electric vehicles sold globally. Chinese companies control approximately 80% of global battery cell production capacity and dominate processing of critical battery materials. In mobile payments, Chinese platforms process transaction volumes dwarfing other countries. Alipay and WeChat Pay together handle over 1 billion users. In 5G telecommunications equipment, Chinese companies Huawei and ZTE are among top global suppliers. In commercial drones, DJI holds approximately 70% of the global consumer market. In solar panel manufacturing, Chinese companies produce over 80% of global supply. However, China faces critical constraints. The semiconductor challenge represents the most significant vulnerability. Advanced microchips require equipment and design tools primarily controlled by companies in the United States, Netherlands, Japan, Taiwan, and South Korea. Designing advanced chips requires software tools primarily made by American companies. Manufacturing requires equipment from Dutch company ASML and American companies like Applied Materials. The most advanced chip fabrication occurs in Taiwan and South Korea. China has invested heavily in developing domestic semiconductor capabilities, deploying over $150 billion. Progress has occurred in mature chip technologies. However, closing the gap in cutting-edge chip manufacturing remains a long-term challenge, requiring breakthroughs in materials science, manufacturing processes, and equipment production. In software, American companies maintain strong positions. Operating systems are dominated by Apple, Google, and Microsoft. Enterprise software is largely controlled by American companies. In aerospace, China has made notable progress with the space station and lunar rovers. However, significant technology gaps remain in jet engines and avionics. The technology competition between China and the United States has intensified markedly since the late 2010s. Trade restrictions, investment controls, and technology export limitations have become strategic competition tools. These measures create pressure for technological decoupling in certain sectors. However, complete decoupling is extraordinarily difficult because supply chains remain deeply interconnected. Despite remarkable progress, China faces significant structural challenges. Demographics present a fundamental constraint. China's population has begun declining. The working-age population peaked around 2015 and is shrinking. The fertility rate has fallen to approximately 1.2 children per woman, well below the replacement level. By 2035, roughly 400 million Chinese will be over 60 years old. This demographic shift creates multiple pressures. Labor costs will continue rising. Innovation tends to correlate with young, dynamic populations. The dependency ratio worsens as fewer workers support more retirees. The semiconductor bottleneck remains acute. China imports over $400 billion worth of semiconductors annually, exceeding oil imports. This dependence creates strategic vulnerability, despite massive investment. Achieving self-sufficiency in advanced semiconductors will require years or decades. The challenge requires fundamental breakthroughs in multiple areas simultaneously. Questions about innovation quality persist. China produces over 400,000 patents annually and publishes over 700,000 scientific papers, both highest globally. However, citation rates and patent quality metrics suggest much output represents incremental improvements rather than fundamental breakthroughs. Transitioning from adaptive innovation to pioneering innovation requires different institutional cultures, greater tolerance for failure, and reward systems valuing originality. Economic pressures create additional constraints. China's economy has slowed from growth rates exceeding 10% to around 5%. Debt levels have increased, particularly in local government and real estate sectors. These economic pressures limit resources for continued large-scale technology investments. Global regulatory pushback affects Chinese technology companies seeking international expansion. Concerns about data security and potential government influence have led multiple countries to restrict Chinese technology products. These restrictions limit market access and create uncertainty for global strategies. China's technological rise is not the result of a single policy or advantage. It reflects decades of coordinated decisions opening to foreign knowledge, expanding STEM education, building dense manufacturing ecosystems, investing heavily in research, and enabling rapid consumer adoption. These pieces work together to create an environment where technology could scale faster than in most countries. Yet, the path forward is not guaranteed. Demographic decline, semiconductor dependence, economic pressures, and global regulatory pushback will shape China's next phase of development. Understanding both the strengths and the constraints provides a clearer view of how technological leadership is formed and how it evolves. If this video helped you see the bigger picture, share which factor you found most influential. Subscribe to FactoPiaX for more neutral, data-driven explanations that reveal how our world truly works. Your curiosity moves this channel forward. See you in the next video. Until then, stay curious and stay with FactoPiaX for more amazing videos.